This is the second lesson in the electromagnetic radiation and optics module. This lesson is going to cover reflection and mirrors. We will do some practice problems on how to calculate if the image is virtual versus real versus convex, concave mirrors, and so forth. First of all, reflection is when light strikes some kind of boundary. Most students think that mirrors are reflection, but remember it can be any boundary. Another example would be a window. This reflection, refraction, or absorption might be visible based on light rays. Another good one is water, and that is why we think that the fish is somewhere else than it actually is, because that is the actual light rays bending when it hits our eyes. Image location. Remember that having two eyes can help us determine the exact location of an object. I put a personal example here. I played softball in college, and one time I got hit in the face with a softball. My eye actually swelled shut, could not see anything out of it for about 2.5 weeks. And my depth perception was off the entire time that I was healing. I was not allowed to play softball, of course, because I couldn't catch the ball because I couldn't exactly determine where that location of the ball is. So that is why having two eyes is very important for depth perception and the location of why we actually see items. Ray model. Notice that we will use rays to extend them as imaginary rays are usually represented by dotted lines and the real rays as solid lines. Imaginary image appears when the two imaginary lines intersect. So we can see here over in our example that when we extend those lines based on that ray diagram, on this side they're dotted. This is where they're going to intersect. Obviously, if we follow the rays on this side, they'll never intersect because of the angles if I actually was drawing straight lines. So that's how we will use the ray model. And remember that real images will appear when the two real rays are going to intersect. And we're going to go through several examples of these. First of all, since I'm talking about virtual and real, let's define some of the terms that we're going to be using. The object distance is the distance from the actual object to the mirror reflection surface. The image distance will be the distance from the image formed by the mirror to the mirror reflection surface. The virtual image is an image produced by an imaginary intersection of light rays, and the real image is going to be formed by the actual intersection of light waves. There are also different types of mirror. We have spherical mirrors, which are curved and made from segments of a sphere. Convex, which is the reflective surface being the outside of the sphere, and the concave, which will be the reflective surface being the inside of a sphere. The law of reflection will follow both convex and concave mirrors, so we can make drawing the images easier by learning a few specific ray rules. Curved mirrors are part of a perfect sphere, and remember that the principal axis is an imaginary line drawn from the middle of the curved mirror to the center of the sphere that it came from. I'm going to be talking about the principal axis here a little bit, so basically I'm going to draw, or do my best to draw it for you. So if we have the mirror here, and if we imaginally visualize the rest of that perfect circle, obviously I'm hand drawing it, the principal axis would be from the middle of the sphere to the actual middle of the curved where it's coming from. So that would be the principal axis there. So again, here's a visual representation of a convex mirror. The sphere is silvered on the outside to form the reflective surface. So a convex would be the outside of the sphere that's being reflected, or the actual mirror is located. And the concave mirror would be the reflective inside is where the mirror is. So I always remember that concave, because of the C right here, means that the mirror is going to be inside because it's a cave. So it's inside the C is where the mirror is. And then the convex will be the opposite of that. Just a little tip to help you remember that. Here is some terminology of the locations. Remember that the focal point is a point on the principal axis where any rays of the light that are parallel to the principal axis will reflect through. The vertex is the center of the curved mirror. The focal length is the distance from the vertex to the focal point. And then the center of the curvature is the center of the sphere that the mirror is a segment of. All right, so if we have light coming on from this side over here, the arrows are showing this is the reflective surface. Remember that the principal axis is coming from that middle of the sphere, which would be over here called the center of curvature. And then we have the focus, or the focal length, will be the this mirror to the actual focal point. So those are some of the terminologies defined. All right, so now if you follow these rules on how to locate the image for a concave, it's going to actually produce a real image for this example. So always use two rays that graphically determine the location of images. So number one, a ray parallel to the principal axis will always reflect through the focal point. So over here, what that is showing us is that here's the focal point. So we have a ray that we're going to draw from the object parallel to the dotted line, which is that principal axis. It's going to reflect through the focal point, and we're going to continue the ray. Now, I should be using a ruler, but it's almost impossible to do that in a computer. So please keep in mind that if you're doing this freehand, you should be using a ruler. And number two is a ray that passes through the focal point will reflect parallel to the principal axis. So we did one parallel first. The other one we're going to take through the focal point first, which is the green line, and then reflect it parallel to that axis. So those two lines are going to intersect at this point. So that would be where the image point will be the point of the intersection where the blue and green arrows intersect. So since it is on this side of the mirror, we know that the image is considered real. All right, so an example of it to be virtual, we would see again that concave, the reflective surface is on that inside. We do the same principle. So we have the focal point here. We draw one line that is parallel to that principal axis that reflects off through the focal point. And then the other one, which if you continue this green line, would be through the focal point here, and then reflected parallel to the principal axis. So now obviously if we continue this all the way and this, they would never intersect. So if that is the case, you're going to extend the lines on the opposite side of the mirror. So we have those imaginary lines that you extend between the blue and the green ones, and we get an intersection on the opposite side. So if it's on the opposite side, that means that the image is going to be virtual. But you do the exact same rules as you would for the real, just where those two rays are going to intersect. So now we're going to look at how to locate the image with the convex or the virtual. So now the reflective surface is on the opposite side, convex mirror. So we do the same thing. A ray parallel to the perpendicular axis will reflect through the focal point. So we're going to go reflect, and the focal point's down here. So we know that it's going to come out this way, but since I'll do the same thing with the second one. We're going to go through the focal point. Again, if you extend right here and reflect right here. So since these two lines would never intersect, we know that we should extend them on the other side. So we do the blue line and then the green line. So the intersection will be over here. And so that is going to be virtual. Please note that convex always produces a virtual and a smaller image as well. So again, we have an arrow of this size on the image will actually be much smaller on the opposite, which would be virtual. All right, here is the mirror equation that we're going to be using to do some of the practice problems with. So make sure you have that in your formula sheet. Make sure that you know that the DO is the distance of the object from the vertex, and DI is the distance of the image from the vertex. So we have an object and an image. That's what the O and the I stand for. Make sure that you pay attention to your sign conversions that you must remember. So the focal length of a concave lens is always positive, and the focal length of a convex lens is always negative. The positive of the object and image are positive if they are on the reflective side of the mirror, and the position of the object are negative if they are on the opposite side of the mirror. So we've kind of already talked about those two in those examples that we just did on the previous slides. You also need to know the magnification equation, which you can see at the top here, and we'll talk about it a little bit before diving into those practice problems. The magnification is either the ratio of the image height to object height on the image distance to the object distance. So remember the object distance and the image distance. Same thing for the image height and the object's height. Can help you solve for magnification. A negative value for the height of the image means that the image is real. So that's just another tidbit to double check when you are doing the calculations. So then this graphic down here shows you definitely different components that we can use to calculate the magnification equation for. All right, so let's dive into the practice problems. It says a 5 centimeter tall object is placed 4 centimeters in front of a concave mirror and produces a real image that is 6.00 centimeters from the mirror. Number 1 says, what is the focal length of the mirror? So we use the reflection equation. We plug in what we know. We obviously don't know the focal length. We do know the object is placed 4 centimeters. So that's the distance of the object plus the distance of the image, which is 6.0. And since it's a real image, we're going to leave it positive. We plug that into the calculator. I don't know why that's showing up so bad. And we should get 1F equals 0.417. So we solve for F, and we will get 2.40 centimeters. And it says, what is the magnification? So all we do is plug in that -6 for the 4. Remember that there is a negative there for the equation. So we should get -1.50, which checks out because it is a real image. It says, what is the height of the image? So we do the same thing for the magnification for height. And rewrite the equation. Let me try that again. HI equals MHO, and so we should get -1.5 because that's what we solved for the second part, times 5, because that's what tells us here in the problem, and we should get -7.50 centimeters. So is the image real or virtual? Real, and the image distance is positive. That's how we know that. And then it's asking if the image is right side up, or upside down. And it's upside down because it has a negative height. So make sure you get those correct. And the last practice problem says a convex mirror with a focal length of 5.0 centimeters has an object placed in front of it. The image was produced 3 centimeters behind the mirror and has a height of 1.5 centimeters. It says how far is the object from the mirror? So we use this formula again. We can rewrite it or plug in what we know. So we have 1 divided by -5 minus 1 divided by -3. Keep paying attention to the signs of where it's given to the problem for the location. We solve for DO, and we should get 7.50 centimeters. The magnification, again, don't forget that negative right there. So we have -3 because of the location divided by 7.5, which is what we calculated here. And we should get 0.400 for the total magnification. Notice there's no units for that. What is the height of the object? So we're going to solve for the object height, which is HO. So we know the image height and the magnification. We plug in what we know, and we should get 3.75 centimeters. And now, is the image real or virtual? Virtual, because remember that convex mirrors always create virtual images. And then, is the image right side up or upside down? It is right side up because it has a positive height. And number 3 says it right here. That is it for the practice problems. Please let me know if you have any questions over this lesson after you watch the recording. Thanks and have a great day.